A spiral filament LED lamp, and I've been waiting for the price of these to come down, and it's not come down. It was quite expensive. It came from an eBay seller called Sea Light Understroke Lights, and it cost £12. So they've got quite a few styles of these, and they all seem to be based on this very long filament that looks quite nice, and it's lit up. Lights very evenly. You can see, up close you can see a slight dottiness around it, but on the whole it's not too bad. And I'm guessing from the fact that the power factor is 0.935, which is it's very good power factor. The power is about 4 watts. That's about all I can really say. The current's about 18 milliamps. I'm guessing that it's a very simple current regulating power supply. And it could be wrong, it might be a switch mode power supply, but with that power factor, it's certainly going to be helped with the long string of LEDs in series, which will add up to quite a voltage. But I'll test that. In fact, I'd like to actually see what the voltage that is now. Is there any reason I shouldn't just burst this right now? I don't think there is. So let's see, what if I took a file and just scraped across the glass? No, that's not going to work. What if I just smashed it? Should I turn the power off? That's it open. Now, see, the main difference here is that if that was an ordinary tungsten lamp, it would have just been going pop and bits have been flying out. Oh, you know, while I've got this open, let's get the meter and measure the voltage. So the voltage, let's put it up to, I'm going to be optimistic here, I'm going to put it up to 1000 volts DC, but I'm expecting in the region, actually I don't know what to expect here. Let's test, make sure the probe's in the right position. The voltage is 253 volts. So doing the maths, now I've already guessed that the series string of LEDs, 253, where is the calculator? This is going to make such a mess, well it couldn't make any more of a mess than I've already made. 253 volts, 253 volts, divided by 3, roughly for each LED, is about 85 LEDs times 2. So I'm guessing there's about 168 LEDs in that strip, because I think they're pairs in parallel. Okay, let's explore further. So, I guess at this point, I have to turn the power off. Okay, someone's asking me why the hoppy meter I tended to use the death adapter in it to actually raise it up. This is a power meter which they've got a sort of universal connector in the front of it, and if you plug in a standard plug, because it's these speaker terminals for connecting mains voltage to, if you try and plug an ordinary plug in, it doesn't go in because the cable is filled in those terminals. This plug actually seems to be quite generously sized in the sense that the cable's up higher and it's more flexible, so it does actually go in sort of okayish. Right, so I'll move that out the way, and I shall open the base of this. Now this is where I'm actually going to have to start getting rid of glass, so I'm going to pause momentarily. Well, time flies when you're having fun, and time has indeed flown. That's been hours. But anyway, here it is. It's very slinky and rubbery. It's very interesting stuff, the way they've made this. I'll go into that later, but at the moment, let's plug this in and see it lit. I had to reinforce the ends with heat shrink when I soldered these wires on because it's so floppy. It's so floppy! So let's bring in the quick test and plug it in. Can I also mention that Andrew has some more of the quick test. He got some in and started selling them on ebay.com, but with the new American and Canadian colours. Where is that? Where is his listing? And I'll show you his listing. He's got about 6 at this point in time. If you want them, you'll have to rush and grab them because he's only getting them in small batches from the UK, and then he's putting the cable on them and selling them on eBay. So quick test in US, Canada wire colours. I think he's probably going to sell out those quite quickly, like he did the last batch. So I've just plugged it into the quick test. I'm just going to plug it in, and it's quite stylish. That is. I'm only going to handle it with one hand because it is potentially live at 250 volts but referenced to the mains, so it's weird, very weird. What's interesting is the current flowing through this is only 10 milliamps. there's a bit of extra circuitry that's eating the rest of the power and wasting it as heat, but that's for a very specific reason. But this is very intriguing stuff. I thought it was going to be stiff. I have to say I thought this was going to be based in the metal strip version of the LED filaments. Do I have any LED filaments up here? Yes, I do. I thought it was going to be based in the sort of metal version of these. I think these ones are the glass ones by the feel of it. Yes, they're the crunchy glass ones, I think. I'm not going to test my luck there. But it's not, because the metal ones, you could bend them in one direction, but they'd fail in the other direction. Mike's electric stuff, Mike showed that when he was covering the filaments as well, how you could bend them over in one direction. And I have seen some lamps that do that. They basically just take one of those filaments and they just fold it sort of over like that, and it creates a little filament in a sort of pygmy lamp style thing. However, let's unplug this now, and I'll show you the circuit board. Just drop the quick test down there. I'm trying to think of things to actually do with this. It's really intriguing, this rubbery filament. Very, very interesting. The circuit board, I'll let you digest this for a moment, looks like this. I shall try and get the rest of that actually in. So if you want to try reverse engineer it yourself, you can either come back to this image or you can freeze it now and take a wee screenshot or something like that. But the chips are SM2082D, and they are the sort of active resistance chips. They're not, there's no switching going on here. It's not high frequency supply. The radio hams will be delighted to know that these produce virtually no noise whatsoever, because all these are doing are acting as resistors. And interestingly, one of them is driving the LEDs and the other one is just driving a couple of resistors. So I'm going to show you the schematic for that now. Anything else that I have to show you on here? Nothing really major, other than the fact that we've got the mains come in. There's a metal oxide resistor across it. Pretty much after that goes to the bridge rectifier. There is a series resistor. And from the bridge rectifier, it's the rectified supply to unsmooth DC, then feeds the resistors and the LEDs. So let's bring in the notepad. We all like the notepad. I think that's a modest exposure level, yeah, so we'll keep it at that. So here's how it works. We've got the mains come in, and it goes through a resistor. Now the resistor is one of those sort of like inrush limiting fusible resistor type arrangements, a metafilm resistor, and its value is 510 ohms, which might sound quite high, but to be honest, everything in this lamp cap is dissipating a little bit of heat just to, you know, because it is a resistive dropper effectively, an active resistive dropper. So there we've got the bridge rectifier. We've got AC in, AC plus, minus, that's going straight over there. We've got the metal oxide resistor. It's a 470 volt one, which if there's a transient, high voltage transient, it will just basically clip that off. It will shunt it to protect the circuitry. The output of this rectifier then gives a positive rail and a negative rail. I'm not going to say 0 volts because 0 volts in the circuitry, but really it's just the negative rail. The LEDs are fed through a diode for a start. Then the circuit splits. It goes through all the LEDs. I'm not going to draw them all because there are 200 LEDs, and that would take quite a while. You would get very bored very quickly. Across that are a resistor and a capacitor. I'm guessing it's an electrolytic capacitor. I'm guessing the resistor is there to discharge the capacitor, just to make sure probably that the lamp turns off quickly without a sort of slow discharge curve, and also to avoid any slight current leakage through dimmers and things, making the LED filaments light up, although to be honest the other resistive arrangement does that as well. That might be a multiple purpose thing. So then that goes down to the value of those 2.2 microfarad, 400 volt for that capacitor, and 330k for the resistor. It then goes down to this active component, which has one connection going directly to ground and the other one going through a sense resistor. This also unusually, not shown in the manufacturer's schematics, has a small capacitor across it. So this component is almost like an electronic variable resistor. It monitors the current flowing through. It's very, recently I was looking at these driverless, well, they call them driverless LEDs. And these resistors, these components do exactly the same thing. They sense the current flowing through this resistor. As soon as it reaches about 0.6 volts, then this starts going up in resistance to regulate the current, a very simple current regulator, but it's also got temperature sensing as well. So if it gets too hot, it can actually wind down as well to a degree itself. But so this thing, normally, this could work on its own. It would just limit the current through LEDs. This would get hot, and it would, if it got too hot, it would just nudge the current down. That's simple. But there's the extra bit in this circuitry, which is two resistors in parallel, which get hot, and they've got their own current regulator chip. But instead of their sense resistor going straight to the ground, like the other one does, it's actually going across here to that position. And I couldn't work that out why they'd done that. I thought maybe it's to save, space in the circuit board. But they could easily have taken it up to the negative rail directly. And then I suddenly realised that what these resistors are doing, what's the value of those resistors? They're the 20k. So 2 times 20k equals, and they're in parallel, so it's 10k total. And what's actually happening here is that when the LEDs are on, and I should elaborate on this a little bit more. The LEDs won't conduct, because there's 200 of them basically wired as parallel pairs of 2, all wired in series. So there's effectively 100 LED forward voltage drops. So it's going to start conducting roughly 240 volts up to a high full current. It would be about potentially 300 volts across that. But that means that in the main sine wave, the rectified sine wave, they're only going to be coming on quite high up in that. So they're only going to be lit for, say, that section of the sine wave. And when they light at that upper section, the voltage across this resistor will rise to the 0.6 volts when it switches into current regulating mode. And that means that circuit's will also rise up to 0.6 volt plus that resistor there, which means effectively when the LEDs are lit, it shuts this bit of the circuitry off as far as I can see. But when the LEDs are off, this circuitry kicks into action, finding its path to ground. And these resistors just dissipate that as heat. And the reason I think it does this is that if the current dropped to 0, then things like triacs and dimmers just might not fire properly. I'm thinking it's possibly to latch the triacs and dimmers and to give the dimmers some current flowing through the light for operation. But I'm pretty sure there's probably other reasons as well. I had a reason in my mind, I've just completely forgotten what it was. But it's an interesting arrangement. Now, the actual strip itself, that's going to bug me now that I've just forgotten what the other thing I was thinking of. The latching of the triacs, that's all I can really think of right now. But anyway, the strip, the actual flexible LED strip, that's not, that was supposed to be 2 symmetrical lines. Just ignore that then, that's rubbish. But anyway, the symmetrical strip looks like this inside. If you actually look at it while it's lit, I had to light it at low level to see this, but you can see lots of little, you know what, I should draw this bigger. I really should, because it's going to make it a lot easier. Okay, here's a really zoomed in image. And what it has is got little pads, pairs of pads, all the way along it. And this is flexible circuit board material. The best thing I can really compare it to is this printed circuit, flexible printed circuit board for the LED tape. And it is like a miniaturized LED tape, except instead of having the LEDs soldered onto it, it's actually got the little LED chips bonded directly to it as far as I can see. and the bond wires going straight on. So these are wired as parallel pairs. So a very thin track comes in from one end, and it loops across like that to the next LED in the parallel, and then this one comes across like that, and that's repeated like this. And then there are these links like this, and it continues on. And basically this is just little pairs of LEDs all the way along, all wired in one big series string, but these are tiny, they're minute. And what they've done then is that if you looked end on, that strip is got the LED chips like that with the little bond wires going across, and the whole lot has had a layer of the gel containing the phosphor put on one side and on the other side, so it ends up looking sort of round. It's so small, you know, I've actually lost it here. I've just buried it under paperwork. But it ends up looking round and floppy, and it is very directional in a sense, in the sense that one side of it is brighter than the other. This side, the side with all the chips on it. But because they've kept the tracks very thin on the printed circuit board material, a lot of light still comes through from the other side. But it's really fundamentally that's it. It's almost like a super miniaturized version of this tape, but with the phosphor gel on either side. And at the ends for the connection, where the little thin circuit board material comes out, where it's quite floppy, they've put on a crimp arrangement round it with a stem, which if you look from the end on, if that's the printed circuit board material, they've folded this little metal staple round it like that, and then the tag comes off to actually bond onto the wires for treating it as a sort of filament in the lamp. So it's really interesting stuff, very interesting indeed. Super simple when you look at the design of it, and I wonder what other applications this is going to find. I suppose really you could have tubular lights with linear arrays like that in it. It's interesting stuff. Yeah, I'm going to have to find something to do with this. It's very, very intriguing indeed. But yeah, that's how those LED lamps with the spiral LED filaments work. It is basically miniaturized LED tape with a resistive current limiter in line. I've just remembered that thing that I'd forgotten, and this is also going to give me an opportunity to draw in the other values here. So that's 100 ohms, and that one was 22 ohms. Now, the other thing that I was trying to remember, which I actually did say in the video, while I was testing this, I put a resistor in series, and I put a 1 megohm resistor in series to run the LEDs at lower intensity so I could count them, because counting them turned out to be very, very difficult. And I tried a 1 megohm resistor in series, and I was expecting them to glow dimly, and they didn't. So then I tried two 1 megohm resistors in parallel for 500k, and it still didn't glow. And then I tried a 100k resistor, and it still didn't glow. And then I tried 5 100k resistors in parallel, 20k, and it still didn't glow. And the only thing I could get it to glow, I ended up putting a capacitor in series with it. And the reason for that is that the other purpose of this here is to shunt leakage. Because if you have a dimmer, it usually has a snubber network across it, and whereas with traditional tungsten lamps, the leakage through that dimmer wouldn't have caused any problems. With these lamps, it does cause a problem. It makes the lamps glow. And while this little resistor across here will get rid of the tiny amounts of leakage you get through capacitive coupling and wiring, it won't solve the problem of the capacitively coupled leakage, deliberate capacitively coupled leakage through the dimmers. So what this does, it effectively acts as a low resistance value and stops voltage going anywhere near where these LEDs would conduct, and that's exactly what was happening. To actually count them once I'd got it glowing, for safety I put a rubber glove on one hand just to actually give some insulation, just in case I wasn't sure if there would be any contact coming out here. And tried to count them, and that was impossible, because as I say, there's 200 and they're slightly staggered and slightly diffused, and they all look very similar when they're lit. So it was lit at low intensity. I took a measuring tape. I worked out that for every 10 millimeters there were exactly 7 LEDs. I'm not sure how they come to that spacing. But the total length illuminated area was 28.5 centimeters. Calculator. So 28.5 centimeters, 28.5 centimeters times the 7 LEDs per centimetre equaled 199.5, 200 LEDs effectively. That's a lot. I wonder how many of these strips actually get rejected. I wonder what the failure rate is. Who knows? But I'm guessing that even if one LED fails, it doesn't really matter because the other one in parallel with it will still light. And these are effectively that I've measured, I broke the circuit and I put the current meter in series and it was 10 milliamps was flowing through this string. Interestingly, I used the clamp meter but didn't believe it, but it was spot on. It was 10 milliamps it was showing. And if you consider that there's two parallel strings then, a series string of parallel pairs, then that's just 5 milliamps per LED. So yeah, I'm kind of miffed that this bit drops so much the power, because if that wasn't there, the power dissipation of this light would drop from about over 4 watts down to about 2.5. It would be much lower. But having said that, it is there for that purpose. It's to make it dimmer compatible. So yeah, oh, the other thing, the name of the company that made this, what was it? The seller was called Sealight, and the actual screw base also had the name Sealight. I wonder if they are actually the manufacturers. It was punched into it. So they actually may be manufacturing them and selling them directly. I'm not sure. Or unless they've just had it made for their particular brand. You can see as I rotate this, it's got a dark side and a bright side, just like the Force. But yeah, really, really neat stuff. I think this could be another random direction that LEDs are going in. It's going to be interesting to see where that goes.